Hi students, welcome to the next session of the subject Engineering Mathematics, Chapter 1 Linear Algebra. Even in this session also we discuss basic concepts followed by examples and followed by some remarks etc. Right? Next definition, upper triangular matrix. Suppose A is a square matrix of size n cross n. We say that this is upper triangular matrix if all elements below diagonal are 0. So whenever all the elements below the principal diagonal are 0, then it is called an upper triangular matrix. Now let us discuss an example followed by mathematical equivalent definition of upper triangular matrix. Suppose I have a matrix like this, A equal to 2, 3, 0, 1. Now in this case, these are my principal diagonal elements 2, 1. Now this element lies below the diagonal elements which is 0. Now what is the position of this element? This is first element in the second row. That is, this is A21 equal to 0. Suppose when you take 3 by 3 example, A equal to, suppose 2, 1, 9, 0, 8, minus 3, 0, 0, 4. Now here my diagonal elements are 2, 8, 4. Now all elements below principal diagonal are 0. Now this is A21. So here A21 equal to 0. This is A31. A31 equal to 0. And this is A32. So A32 equal to 0. Now in this case, what is the relation between indexes I and j? Here this I greater than j. I dominates j. 3 greater than 1. 3 greater than 2. Therefore, a square matrix A is said to be upper triangular if all elements below diagonal are 0, or equivalently we can write like this: Aij equal to 0 for all I greater than j. For all I greater than j. See here, if all elements below diagonal are 0, then it is called an upper triangular matrix. It does not mean that all elements above and along the diagonal are non-zero. So they can be 0 also, but I need at least all elements below diagonal are zeros. So if a matrix fulfills this requirement, then it is called an upper triangular matrix. Note this point. A square matrix A is said to be upper triangular. A square matrix A is said to be upper triangular if all the elements below the diagonal are 0. A square matrix A is said to be upper triangular if all the elements below the diagonal are 0. That is, small aij equal to 0 for all I greater than j. Aij equal to 0 for all I greater than j. Note down these two examples. Next definition is lower triangular matrix. Now in the previous, if all elements below diagonal are 0, it is called upper triangular. Now in this case, all elements above diagonal must be 0. So if all elements above diagonal are 0, then this is called a lower triangular matrix. Now let us have some examples. We start with the 2 by 2 example. A equal to 2, 0, 9, 3. A equal to 2, 9, minus 3, 0, 0, 0. I can have 0 also here, no issues. 8, for example, 11. Now in this case, My diagonal elements are 2, 3. Now elements above diagonal are 0. In this case, A1, 2 equal to 0. This is second element in the first row. Here I is less than j. Now here my diagonal elements are 2, 9, minus 3. Now all elements above diagonal are 0. This is second element in the first row. So therefore this is A12 equal to 0. And this is third element in the first row. So the notation is A13 0. This is third element in the second row, A23 equal to 0. So I less than j, I less than j, I less than j. So the equivalent definition is a square matrix A is said to be lower triangular if all elements above diagonal are 0. Or equivalently, we can write like this. Aij equal to 0 for all I less than j. Note this point. A square matrix A is said to be lower triangular. A square matrix A is said to be lower triangular if all elements above diagonal are 0. If all elements above diagonal are 0. That is, small a is equal to 0 for all I less than j. A is equal to 0 for all I less than j. Note down these two examples. This definition is diagonal matrix. Previously, we have seen upper triangular matrix as well as lower triangular matrix. Now, let us combine the properties of these two. We get a new matrix that will be called as diagonal matrix. In simple words, a square matrix A is said to be diagonal matrix if it is both upper triangular and lower triangular matrices. Got it? So, it must be both upper triangular as well as lower triangular. So, in that case, it is called a diagonal matrix. That means all elements above and below diagonal are 0. In that case, the matrix is called a diagonal matrix. Examples: A equal to 2, 0, 0, minus 3. 3 by 3 matrix example, A equal to 1, 2, 0. Here elements are like this, 0, 0, 0, 0. Therefore, in this case, all elements above diagonal and below diagonal are 0. Here also, the diagonal elements are 1, 2, 0. All elements above diagonal and below diagonal are 0. So, it is both upper triangular and lower triangular. The same case repeats even for second example also. So, both are diagonal matrices. A square matrix which is both UT and LT. A square matrix which is both UT and LT is called a diagonal matrix. Write these two examples, this and this. As definition, scalar matrix. When you compare previous definition, it is upper triangular as well as lower triangular. That means all elements above diagonal and below diagonal are 0. So we need not have any restriction on diagonal elements. Now in this context, we need to put some restriction on diagonal elements. So above diagonal, 100% guarantee that elements are 0. Below diagonal, elements are zeros. And diagonal elements must be same. That means one element repeats many number of times. All diagonal elements are fixed to some constant k. And above diagonal and below diagonal are 0. In that case, it is called a scalar matrix. Now, how to define this? A diagonal matrix in which all diagonal elements are equal is called is a scalar matrix. How to define this? A diagonal matrix in which all diagonal elements are equal to some constant k. That is called a scalar matrix. Let us have few examples. Suppose I have A equal to 2, 0, 0, 2. Now here diagonal elements are 2. It is both UT and LT. So it's a diagonal matrix and diagonal elements are same. B minus 1, 0, 0, 0, 0, minus 1, 0, 0, 0, minus 1. It's a diagonal matrix and diagonal elements are representing single quantity. So it's a scalar matrix. It's a scalar matrix. A diagonal matrix. A diagonal matrix in which all diagonal elements are same. A diagonal matrix in which all diagonal elements are same is called a scalar matrix. A diagonal matrix in which all diagonal elements are same is called a scalar matrix. Note down these examples. Example 1 and example 2. Next definition, identity matrix. Just now we have seen a scalar matrix. So what is scalar matrix? A diagonal matrix in which all diagonal elements are same. So all diagonal elements can be 2. All diagonal elements can be 1 by 6. All diagonal elements can be minus 0.7. But in this case, it must be diagonal matrix, scalar matrix, and in which all diagonal elements are restricted to 1, the number 1, constant 1. So a scalar matrix in which all diagonal elements are restricted to 1 is called an identity matrix. Symbolically, it is denoted by IN cross N or IN. Suppose when you take N equal to 1, then the matrix is called I1. So it contains a single quantity, it is 1. Suppose if N equal to 2, then it is called as I2 symbolically. So here diagonal elements are 1, 1 and rest of the elements are zeros. Suppose if N equal to 3, the matrix becomes I3 equal to 1, 0, 0, 0, 1, 0, 0, 0, 1. Therefore, this is basically a particular scalar matrix. It is a particular case of scalar matrix and all diagonal elements are restricted to 1. What is the specialty of this matrix? There is one advantage with this matrix. In generally, suppose if I have two operations, one is plus, another is multiplication. In terms of numbers, when I add 0 to all the real numbers, I will get same constant. That is, a plus 0 equal to a for all a belongs to r. Here r represents set of real numbers. Suppose if plus is replaced by dot, then 0 must be replaced by 1. A dot 1 equal to a for all a belongs to r. That means when you multiply all real numbers with particular real number 1, we are getting same number. In the same context, when you add 0 to all real numbers, you are getting same number. That means these elements are called as identity elements. So that is 0 is called identity element with respect to plus. 1 is called identity element with respect to dot, because when I take two different operations, identity element is changing. So that's why 0 is called additive identity and 1 is called multiplicative identity. So if anyone asks you what is the identity element with respect to this particular operation, be cautious. In terms of addition, it is 0. In terms of multiplication, it is 1. So this is regarding numbers. In matrix concept, when you multiply all matrices with identity matrix IN, you will get the same matrix. That's why it has named as identity matrix. Got it? Note this point. A scalar matrix in which all diagonal elements are 1. A scalar matrix in which all diagonal elements are 1 is called an identity matrix. Is called an identity matrix. It is denoted by In cross n or In. In cross n or In. Examples, you can write I2, I3. See the sequence of last 3 to 4 definitions. At first we started with upper triangular matrix and then lower triangular matrix. When you combine these two, you will get diagonal matrix. When you take a particular diagonal matrix, you will get scalar matrix. When you take a particular scalar matrix, you will get identity matrix. So just follow the sequence. Definitions will be very clear and examples will be so simple. Next concept, trace. Suppose A is a n cross n matrix. Since it is a n cross n matrix, we have n diagonal elements. Assume that my n diagonal elements are A11, A22, A33 and so on, comma, ANN. These are my diagonal elements. Now add all these diagonal elements, we get some constant and that will be called as the trace of this matrix. This is my n cross n matrix A with these diagonal elements A11, A22, A33 and so on, ANN. Add all these diagonal elements, I will get some constant and that constant is called trace of this particular matrix and this is denoted by this TR of A. This is given by A11 plus A22 plus A33 plus and so on plus ANN, and this is nothing but summation I equal to 1 to n AI. So trace of A equal to this. Write the definition. Let A be any n cross n matrix. Let A be any n cross n matrix. So the trace of A is defined as sum of diagonal elements of A. The trace of A is defined as sum of diagonal elements of A. So it is denoted by TR of A. It is denoted by TR of A. Therefore, TR of A equal to A11 plus A22 plus and so on plus ANN. TR of A equal to A11 plus A22 plus and so on plus ANN. That is equal to sigma I equal to 1 to n AI. Now based on this definition, let us make two important points. One is the trace of skew symmetric matrix and another is trace of identity matrix. As we all know, what are the diagonal elements of skew symmetric matrix? 0. So add all zeros, you will get 0. So one important remark from this definition is trace of a skew symmetric matrix is 0. Right? And second point is, what is the trace of I2? It is exactly 2. Because in a 2 by 2 identity matrix, there will be exactly 2 ones. Trace of I3, 1 plus 1 plus 1, 3. So in general, trace of IN is n. So two important points are trace of A equal to 0, where A is a skew symmetric matrix. And second point is trace of IN equal to n. Note these 2 points. The next concept is properties of trace. Suppose A comma B are two n cross n matrices equal size. Then A plus B is possible. Its size is again n cross n. Now I can discuss the trace of this matrix. So trace of this matrix A plus B is trace of A plus trace of B. If it is minus, we get minus sign. Next one is trace of Ka. K is constant, A is matrix. So K can be taken before trace. So this is K times trace of A for any constant K. Property 3. Trace of A is same as trace of A transpose, right? See, when you transpose a matrix A, diagonal elements will not change their locations. A11 will be in the same location. For trace, only diagonal elements are required. So trace of A remaining elements will change their locations, but diagonal elements will not change their locations. So in that context, trace of A and trace of A transpose will be same. And fourth property is trace of product of two matrices A dot B. So trace of AB is same as trace of BA. Even though AB and B are different, but their traces will be same. So if I generalize this, if I extend for three matrices to trace of ABC, assume that all matrices are of same size n cross n, then I can multiply ABC. I will get new n cross n matrix, so that I can discuss the trace of this matrix. So trace of ABC equal to trace of ACB. This is same as trace of BCA. This is same as trace of BAC. And this is same as trace of CAB. And this is same as trace of CBA. Now at this point, we have 6 different combinations. So basically all these are nothing but permutations among 3 symbols ABC. I have 3 symbols. In how many ways I can arrange 3 symbols? In 3 factorial different ways. Just I am changing the positions of matrices. See here ABC, next ACB, BCA, BAC, CAB, CBA. All these are nothing but permutations among 3 symbols ABC. In our context, ABC are matrices of same size n cross n. Therefore, traces of all these combinations will be same. Right. Note all these points. Suppose A is an n cross n matrix. We say that this is orthogonal if it satisfies the property A into A transpose equal to A transpose into A equal to IN. Just multiply original matrix with its transpose. Multiply a square matrix with its transpose. Even in the reverse direction also. So both matrices must be equal to identity matrix. So whenever A into A transpose equal to A transpose into A equal to IN, then this is called an orthogonal matrix. Let us take an example. Suppose I have A equal to cos alpha minus sin alpha cos alpha. Alpha is some real number, general 2 by 2 matrix. Now let us calculate A into A transpose. This is cos alpha minus sin alpha cos alpha into the transpose of this matrix. This is cos alpha sin alpha minus sin alpha cos alpha. Now let us multiply these two. So multiply first row with the first column of this matrix. Cos into cos square alpha, minus into minus plus, cos square alpha plus sin square alpha, it is 1. Next, multiply this with second column, cos alpha sin alpha minus sin alpha cos alpha, it is 0. Similarly, the second row becomes 0, 1. In the similar way, you can easily verify that A into A transpose is also same as 1, 0, 0, 1. Basically, this is I2. And even this is I2. So, in this context, A into A transpose equal to A transpose into A equal to I2. So, this is an example of a 2 by 2 orthogonal matrix. See, the specialty of this matrix is it is not a single matrix. When you frequently change alpha values in the entire x-axis, so you will get different matrices. Suppose when you take alpha equal to, suppose if you take alpha equal to 0, then this matrix A is nothing but 1, 0, 0, 1. So it is an orthogonal matrix. Suppose if alpha equal to pi by 4, then the matrix is restricted to this 1 by square root of 2 minus 1 by root 2, 1 by root 2, 1 by root 2. So all these are examples of 2 by 2 orthogonal matrices. Write the definition. A square matrix A is said to be orthogonal. A square matrix A is said to be orthogonal if A into A transpose equal to A transpose into A equal to In. A square matrix A is said to be orthogonal if A into A transpose equal to A transpose into A equal to In. Work out this example. Next concept, determinant. Suppose A is an n cross n matrix. Now the data of this matrix is denoted by det A or symbol mod A. This is the symbol for determinant of a matrix. Either det A or mod A, we can use this. Now before discussing the definition of det of a square matrix, let us use some mathematical formula and then we can discuss cofactors followed by determinant of a square matrix, right? Let us start with the smaller versions. Suppose if n equal to 1, I am dealing with 1 by 1 matrix. Then A equal to x, 1 by 1 matrix. It is a 1 by 1 matrix. A contains single element, let it be x. In this case, data of this matrix equal to x itself. Suppose if n equal to 2, implies the matrix A is this. This is A11, A12, A21, A22. So in this context, the data of this matrix is product of diagonal minus product of non-diagonal elements. Multiply these two minus multiplication of these two. So this is A11 into A22 minus A21 into A21. So product of diagonal elements minus product of non-diagonal elements. It works only for 2 by 2 matrix. But when I go for larger dimensions, then I can have some different formula. After that, we can generalize the general definition of determinant of a square matrix. Suppose if n equal to 3, then I am dealing with a 3 by 3 matrix. So I am going to write general 3 by 3 matrix A11, A12, A13, A21, A22, A23, A31, A32, A33. Now in this context, we have 3 rows and 3 columns. We can expand the data of this square matrix in 6 different ways. I can expand its det value by using first row. or by second row or by third row, or by using first column or by using second column or by using third column. So if you want to find determinant of a 3 by 3 general matrix, we have 6 different ways. Whatever the way you follow, final result must be same. Now let me write the formula to expand its det value by using first row. Therefore, in this context, the det of this matrix is small a11 into capital A11 plus a12 into capital A12 plus small a13 into capital A13. Now let me list out what is this capital letters, capital A11, A12 and A13. This capital A11, this is nothing but cofactor of small a11. This is cofactor of this and this is cofactor of this. So capital letters I am using to find the cofactors of small alphabets. This is nothing but minus 1 whole power 1 plus 1. Minus 1 is common symbol. 1 plus 1, add these two indexes into determinant of. Now this A11 is available in the first row and first column. Eliminate this. So it is present in the first row and first column. When you eliminate this, we will get this remaining 2 by 2 submatrix. So I will find the det of this 2 by 2 submatrix. So this is A22, A23, A32, A33. Now this is minus 1 whole square plus. So det of this 2 by 2 block according to this rule, this is A22 into A33 minus A23 into A32. In the similarly, I can write capital A12. This is cofactor of small a12 and this is given by minus 1 whole power 1 plus 2 into determinant of. This small capital A12 is cofactor of this. It is present in the first row and second column. So eliminate the row and the column in which the element is present. A12 is available in the first row and second column. When you eliminate this, we will get the remaining the submatrix A21, A23, A31 and A33. So therefore this is determinant of A21, A23, A31, A33. So this is minus 1 whole cube, anyhow minus 1 into expand its det. So this is A21 into A33 minus A23 into A31. So this is cofactor of this element. In the same way, the cofactor of the next element is capital A13. This is cofactor of small a13. And this is given by minus 1 whole power 1 plus 3 into det of this particular block. So this is A21, A22, A31, A32. Now like this, we can expand the determinant of any general n-cross-n matrix. Now you can see in this formula, we have multiplied first row element with its cofactor plus second element is multiplied with its cofactor plus the third element is multiplied with its cofactor. That means what we have done is we have selected first row and we have found the cofactors of all these elements and multiply each cofactor with its element and in between these values apply plus symbol. So therefore this is nothing but the determinant of a square matrix is given by the sum of products of, here we have plus symbols followed by multiplication symbols, the sum of products of elements of any row or any column along with their cofactors. That is called determinant of a square matrix capital A. So like this, you can find the determinant of general n-cross-n matrix. You can go for 4 by 4 matrix, 5 by 5, 6 by 6. This is the standard procedure to find the determinant of a general n-cross-n matrix. Note this point. Let A be any n-cross-n matrix. Let A be any n-cross-n matrix. To stop, the sum of products of elements of any row or column, the sum of products of elements of any row or column along with their cofactors is called determinant of capital A, is called determinant of capital A. It is denoted by det A or mod A. Det A or mod A. Now write all these points. This is point 1 and this is point 2, point 3. After this, continue these steps. This is the end of this session. We continue examples followed by shortcuts of determinants maybe in the next session. Thank you so much.